All right, lesson 4.5, Newton's third law of motion called action-reaction. And on the worksheet number 1, which is pretty easy, you'll see, and then do number 3 and number 4 for the calculations. Now, let me erase this. I was doing some chemica. All right. Now, this is a fun law, an interesting one that I'll go over. First, I kind of have to start off and do a little bit of just some explaining some conceptual stuff, some things that might be like a multiple choice question. Well, the first law of motion is inertia. An object will stay in the same state of motion until or unless a force acts on it. So this little ball, if it's at rest, compared to me, it will stay at rest until or unless a force acts on it. I can let go of it and it will fall down. Or if it's moving, it will continue going at the same speed, same direction, until or unless a force acts on it. Now, on the Earth, the air would slow it down, and gravity would pull it down. Okay. If it's in outer space, no gravity, nothing around, it will continue to move on in a straight line forever. Okay. Now, law number two says is F equals ma. Is that the a mass, when a force is exerted on a mass, I'll have to write down. When a force is exerted on a mass, the mass will accelerate. It's important to know. Now, the amount of acceleration depends on the mass. Obviously, a big mass will have a small acceleration. A small mass will have a greater acceleration. And of course, it's directly proportional to the force. So more force means more acceleration. Well, and it's inversely proportional to the mass. Having a great mass means you don't have as much acceleration. So that's kind of two ways to look at it. How does mass affect the force? How does it resist the force? The third one is called action-reaction. And you probably have heard about this before. It says that whenever, well, here's the way I like to write it or state it. I'll just use it for A and B for a moment. Let's say that object A collides with object B. Okay? All right, it says, I'll use A and B. Whenever one object, like A, exerts a force on the other object, obviously if somebody ran into you, they would be putting a force on you. Okay, so say that someone is running at you and boom, they hit you. Okay, like football, they're going to tackle you, they hit you. They hit you. If one object puts a force on another object, whenever one object exerts a force on the second object, the second object puts an equal but opposite force back on the first object. So what does that mean? If someone runs into you and they hit you with a force of 40 pounds, okay, well, that means you also are putting a force of 40 pounds back on them. If A puts a 40 Newton force on B, at the same moment, B is putting a force of 40 newtons backwards on A. Now, this is a neat thing. We can see this happening, or you can kind of understand it. And I'm trying to do two things at once, get my computer. I got to put it to sleep, or it'll suck up the dust from the chalk. Actually, there's some examples down at the bottom, and I'll talk about it. I'll skip the dog and the wall thing and all that. You could run into a wall. Obviously, we think about this. When you run into the wall didn't hit you, right? You hit the wall, but you got hurt because you got a force put on you too. That might sound kind of strange, but you were the one that was moving. You put the force on the wall. The wall, as it resisted, hopefully, or even if you broke the wall, if it partially resisted you, the force you put on the wall will equal the force it puts on you. That's an important thing to know. Okay, so here it helps us in some calculations. It says an ice skater pushes on a rail. So if you've ever skated before, or it could be ice skate or roller skate, just say our little friend Lily, she's on skates. It could be on a skateboard too. How about that? It doesn't have to be. It could be a skateboard. But say that she's pushing on a rail. Well, I don't know how I put a rail. I think like an ice skating rink or something. But if she pushes the rail, for the wall against the wall, is the wall going to move? No, she's going to move. So she pushes on the rail. She's putting what we call the action force, but the reaction force is the rail is putting that same force back on her. So she might put, I don't know, 100 Newton force on the wall. The wall puts 100, or you might say negative 100 Newton force back on her. One will be positive, one will be negative. Okay? A pitcher throws a baseball. All right, now I don't know a good way to, I might not be too good at drawing this, but is it like her arm's wrong or whatever? So here she has a ball. Give her a little baseball cap on her. Okay, so that's not too, what is a mess? That's supposed to be her arm. What was that? Oh, that was her baseball cap. Oh, whatever. There's her cap. Okay, she wants to have the cap on. But the point is, as she throws the ball, you even see as a pitcher when they throw how they come back and how they come forward, like the way and down. You might think that's kind of strange. They're throwing that thing so hard because if she puts on this ball, I don't know how I would draw that, but the ball, if she put I don't know, she's probably not going to throw 90 miles per hour, but we'll just say she can because she's super lily. Okay, but if she throws 90, those pitchers that throw like 90 mile per hour baseball, they throw that ball 90 miles per hour, okay? Well, that means she's putting a force on that ball to get that ball moving 90 miles per hour. Well, let's say I don't know what that force is. Let's just put like 500 newtons. Let's make up some number. That's probably not even enough. It's actually, it's not just the force, but it's over how long are you putting that force too. That matters as well. How quickly can you put that force? So that's another factor. We're not really going to get into that. But if she puts a force of 500 newtons on the ball is also putting a force of 500 back on her. We know that's true. Pitchers in baseball, when they pitch, they can't pitch like every day. They pitch one day and it does a lot to the muscles, the ligaments, everything in your arm. You got to be in amazing shape. Probably a lot of money for insurance and medical to keep you in good shape and good conditioning and everything. So it puts that on your arm. It takes a few days for your arm to heal back after doing all these 90 mile per hour balls, because every time you throw that ball, you're getting that same force on you, on your arm, your shoulder, and everything. So they know how to, I don't know that, I'm sure that baseball pitchers, they know how to position themselves correctly, that do the least harm to them and put the most force they can on the ball. And that's why they might look strange at how they move and the positions they take. Interesting also, if some of the best pitchers, if they threw that ball as hard as they could and they didn't lean down or bend over, they would fall backwards. They would fall back from the ball force on them. Okay, here it says, a small ball is full of bowling balls. So here's one that I like. A small boat is full of bowling balls. Okay, so watch this. So here's a boat, and we'll say we have all these bowling balls, and this thing has just made it. It's not sinking. And here we have Lily again. She's in the boat. Now, here's the deal. Think about this for a minute. So if she's in the water and has all these bowling balls, if she throws a bowling ball this way, she throws the bowling ball she throws it. Boom. She threw the ball, and here it is flying in the air. That doesn't look too good. She threw the bowling ball. Well, she's throwing the bowling ball, and it's true, the bowling ball's moving. But what about her? Is she going to be still? No. Every time she throws a bowling ball, she's going to move. She's going to move, isn't she? And if she threw it faster, and if there were two people, maybe her friend, her brother was in there throwing them, they would be every time they throw the ball, they would get that ball moving across. Isn't that amazing? Well, that idea and that concept is what engineers used when they made rockets and rocket engines. And like for example, for an airplane or a jet, I'll just put a jet. I don't know how I'm gonna draw a jet there, but no, I'm always not so good at drawing a jet. I can draw it like a rocket or something. Okay, I don't know how if I just draw a rocket. It looks like I don't know what that is, a shark or a missile or what is that thing? But we see this stuff coming out the back. Well, here's the deal. Here's what I wanted to show you. The chemistry part of this is you have liquid fuel inside here. All right? The liquid burns. And when the liquid molecules turn into a gas, they don't get larger, but they spread apart completely. They break. So they go from having a small volume, like let's just say that you had 1 liter of gasoline, that when you burn it to fuel, it might turn into like 100 liters of gaseous gas. 100 liters of liquid fuel turns into 100 liters of gaseous fuel. That's amazing, 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 amazing force. So what's happening is it's forcing, as it burns the fuel, it's forcing particles out the back, out the jet. And this every little atom, every little air molecule, we'll say air could be, it could be carbon dioxide even. That's one result you get when you burn fuel is carbon dioxide and water vapor. It could be shooting water molecules and carbon dioxide molecules out of the jet, the same jet that could power, like I said, a missile, or it could also be an airplane or a rocket. But it shoots those out the back, just like the same way that this is shooting out the bowling balls. These particles, it's putting a force on all of these. Every little molecule it puts a force on, and that molecule puts the same force back on the rocket. And that's how it gets to going. So here's the interesting thing. An airplane in the air, in the Earth's atmosphere, as it shoots out those things, the jet, it moves along, but the air slows it down. Okay, so the air will slow it down eventually, and gravity will pull it down. So you have to keep, doing the fuel and all that to keep going. But if you are in outer space, there's no air resistance and there's no gravity. So in outer space, a jet, all it has to do is just shoot out all the fuel. I think I mentioned this, and then it can just turn off. And that thing will be moving at the same speed and at the same direction infinitely, or until or unless a force acts on it. So you don't need a whole lot of fuel to go from here, we'll say, to Mars. You won't need a whole lot of fuel because you just need enough fuel to get fast enough that'll get you there in a reasonable time. That people say it could probably be like close to I can't remember, a year to get there, maybe a year to get back. Well, anyway, you'd have to have just enough, fast enough. You would have fuel if you needed it, and to get back you'd need fuel, but you wouldn't need to burn any fuel any more than that. So those are all a bunch of them. Now, there's one more. It's not the most. To talk about this one is like, I always want to hear about it, but I'm not going to ignore it. But obviously, when a bullet is shot out of a gun, the same thing. Now, I don't know how I can draw a gun, or if I draw a rifle, or whatever it might be. Just say if you have like a rifle. That's not a rifle. I don't know. I'll draw a gun. Kind of like this. Put the place where the trigger of it is. And then there's a barrel. And there's some problems where we'll talk about the barrel of the gun and all that. We'll just say something like that. Well, I'll think more flat. Doesn't really look three-dimensional. But anyway, the bullet inside here, let's just let the bullet be orange, I guess. Let's say here you have the bullet. And then here you'll have gunpowder. Okay? Now, actually, it'll probably be way back here. Well, I don't know how to do it. Like I said, I'm not an expert with guns or anything like that. But back here, you caught the trigger, then boom, you'd hit it, it would snap, and it would push. But when you hit that, it's kind of like those little firecracker toys, whatever, not really toys, but kids will throw them, snap pops, and boom, they explode or whatever, because it's like gunpowder. It's like that, a little explosion will occur. Well, a chemical explosion happens in here too, but it's much greater. And that when you light that fire, the gunpowder, it goes from being a solid powder, kind of like in the jet engine, to a gas. Boom, and it just pushes that bullet out really quickly. But the force applied to the bullet is the same as the force. The force that the exploding gunpowder applies to the bullet is the same that the bullet applies back to the gun. So that's why whenever you see, and mainly it's been from a movie, I'm sure, I don't think too many people have seen this happen in person, but maybe on some videos you may have seen some stuff. But when someone shoots a gun, what happens is the gun, they say recoils, it pushes back. So you have to hold it a certain way, especially if it's a rifle or a bigger, like a machine gun or something. You got to really hold it. That gun will move. Every time a bullet is shot, you're putting a force on the bullet. Well, that bullet is putting the same force back on you. Now, since you're such a big mass, having the force on you is going to move you a little bit, but that little small bullet is going to propel it like incredibly ahead. So anyway, this is just an intro, the beginning part, and I'll come back and show you the calculations in a moment, though.